information like X-ray absorption, fine structures, for example, for ice samples?
So I didn't take that data, but you can email Alexander. Do you want me to get you I can post in the chat the corresponding author for that paper, and then you can email him. It should be available. It's not. It might even be in the paper itself. I'm not sure if they did it. It's in one of those journals though where they say you have to give it up. So we should be able to get you the data.
Okay, thank you very much. Okay, so now let's move to the next speaker. Thank you, Craig. Next speaker is Professor Shigeaki Morita from Osaka Electrocommunication Universities. To keep his presentation time, I will just introduce only title, Concentration-Dependent Near-Infrared Spectra of Water, Aprotic Organic Solvents Binary Systems. So if you are ready, please start, Professor Morita.
Okay, thanks, Professor Takeuchi. So I'm Shigeaki Morita from Osaka Electrocommunication University. First of all, it's my great pleasure for having this presentation today. And I acknowledge Professor Tsenkova for useful discussion recently. And today I'm going to talk about the concentration-dependent near-infrared spectroscopy applying for the binary systems using water and aprotic organic solvents. Here we can see 5 chemicals: acetonitrile, acetone, and dimethylformamide, dimethyl sulfoxide, and pyridine. These are the typical aprotic organic molecule that is no OH group in the structure. Therefore, these chemicals are almost transparent in the OH stretching region. So we can observe pure information of water for the binary systems. So this is a schematic illustration for the experimental setup. We apply the hyphenated method LCNIR, that is liquid chromatography was used for the pump, and near-infrared spectrometer was used for the detector. In this case, we apply the gradient system, that is 2 liquids, water and organic solvents were mixed as a function of time, and the concentration dependent information was measured by the spectrometer using this type of spectrometer. So in this case, we measure the concentration dependence. In that case, the LC column was taken off from this system. In the liquid chromatography, we generally apply such detectors. For instance, UV visible, fluorescence, reflective index, conductivity, and so on. And we can consider such a possible application. For instance, NMR, Raman spectroscopy, mid-infrared spectroscopy. Now we can consider the possibility for the detection by using the near-infrared spectroscopy. Recently, it becomes lower price and it is XH bond sensitive, and we can use just as the appropriate path length, such as 1 millimeter. So this is a typical result for the LCNIR. This is a result of the sample of water using the mobile phase of acetonitrile. In this case, we apply the LC column as C18. It is a typical hydrophobic column. In the case of ultraviolet visible region, almost no signal was detected because the water and acetonitrile has electron transition below 200 nanometers. In contrast, in the near-infrared region, we can obtain the signal arising from water like this. And this is a chromatogram of the water using LCNIR. So let's move to the gradient LCNIR. In this case, we apply such the gradient program. Initial 5 minutes, the water was transferred into the cell, and next 10 minutes, the concentration of water was controlled like this. And finally, last 5 minutes, the only organic solvent was transferred into the cell. And this is the obtained spectra, and the area intensity was plotted like this. This figure shows the spectral variation almost similar to the gradient program. So this is a result for the concentration-dependent near-Earth spectroscopy. These 5 aprotic solvents were mixed with water. The top one for each figure represents the near water. It is volume fraction of water is 100%. And the bottom one is a neat additive. That is volume fraction of water is 0%. We can see almost no contribution from the additives can be seen for the all the 5 organic solvents because of no OH group in the structure. And it is interesting. In the case of acetonitrile, shows gradual higher wave number shift in the waveform arising from water. On the other hand, in the case of pyridine, the waveform of water gradually shifts to the lower wave number region. In order to clarify this spectral variation, we calculate the center of gravity of the waveform. How can we calculate the center of the gravity? And that is the first moment. First moment is calculated like this equation. That is a position of the center of gravity. Was calculated like this. This is a plot as a function of volume fraction of water. The top one is a pure water. A pure first moment of pure water is almost this wave number. And in the case of acetonitrile and acetone, the first moment gradually shifts to the higher wave number. On the other hand, in the case of 3 chemicals, shows gradually shift to the lower wave number. It is interesting. In the case of acetonitrile and acetone, have the smaller donor number in comparison with the water. On the other hand, these 3 chemicals, N,N-dimethylformamide and dimethyl sulfoxide pyridine, has a large number of donor number in comparison with water. What is donor number? Donor number is a quantitative measure of Lewis basicity. A donor number is defined as a negative enthalpy value for the one-to-one adduct formation between a Lewis base and the standard Lewis acid. In this case, antimony chloride in direct solution in the non-coordinating solvent, that is 1,2-dichloroethane with a 0 donor number. It means in the case of these 3 compounds, relatively strong base in comparison with water, while acetonitrile and acetone is relatively a weak base in comparison with the water. In order to clarify this spectral variation, we apply the multivariate curve resolution, MCR. That is a calculation obtain the pure component spectra as well as concentration profiles, assuming the linear combination of these components. In order to calculate this spectral variation, we apply the Python program using the MCR library named PyMCR. This is a result for the MCR using the acetonitrile. In this case, this is a lower basicity chemicals having the higher wave number shift. These are the result of MCR. First component looks almost similar to bulk water having the peak maximum around this wave number, shows concentration profile like this. Horizontal axis represents the water content and the right end point is a pure water, left side is a pure acetonitrile, and the concentration profile of this spectral shape shows gradually decrease with decreasing the water content. On the other hand, in the second component shows the peak maximum around 7,000 wave number. This concentration profile represents like this almost zero intensity at the right side, gradually increase with decreasing the water content and having the peak maximum around 63% of water, and then gradually decrease the intensities. So this figure shows the density plotted as a function of water content. It is interesting. Red point is measured by picnometer, and blue one is the ideal line, assuming no interaction among water and acetonitrile molecules. The decrease of the measured density compared to the ideal line represents the expansion of the solution by inducing the mixing. Bottom one is the delta law, is the subtraction of the experimental data from the ideal line. That is the decrease of the density by mixing shows minimum point around 60% of water. This minimum shows almost similar percentage of water finding in the MCR result. In the case of dimethyl sulfoxide, this is a high basicity chemical showing the lower wave number shift. Almost shows similar waveform in the first component. It looks almost similar to the bulk water, gradually decrease with decreasing the water content, and a second component shows the peak maximum around 6746 wave numbers, and this concentration profile show like this. As the pure water, the intensity is almost zero and gradually increase with decreasing the water content, and peak maximum around 81% of the water and gradually decrease. And it is interesting. The density of the mixture of the water and dimethyl sulfoxide has a positive curvature for the density plotted as a function of water. It means that the contraction of the solution inducing by the mixing of water and dimethyl sulfoxide. Bottom one is a plot of the delta law, represents the increase of the density, shows a maximum around 70% of water. Looks almost similar to the maximum of the second component evaluated by the MCR. So this figure summarizes the 5 aprotic organic solvents. In the case of low basicity compounds, acetonitrile and acetone shows, it is interesting, negative curvature, decrease of the density represents expansion of the mixture, while in the case of N,N-dimethylformamide, dimethyl sulfoxide, and pyridine, these three compounds have relatively high donor number, representing the more strong base compared to the water, shows positive curvature. Positive curvature represents the increase of the density, and is the evidence of the contraction of the mixture induced by adding the aprotic solvents. So this is a summary. Concentration-dependent near-infrared spectra of binary mixtures were measured by means of the gradient LC-NIR system. 5 aprotic additives were measured with water, respectively. Acetonitrile and acetone show higher wave number shift of the OH stretching band, while N,N-dimethyl dimethylformamide, dimethyl sulfoxide, and pyridine show lower wave number shift. So it is likely that DMF, DMSO, and pyridine, which have large donor number compared with water, act as electron donor, that is best, to the hydrogen bonds network in water cluster and enhance the hydrogen bond structure, that is contraction of the solution or exothermic mixing. In contrast, on the other hand, acetonitrile and acetone which have smaller donor number compared with water, break the hydrogen bond structure among water molecules. That is expansion of the solution or exothermic mixing. My talk today is that all, and thank you for your attention.
Thank you, Professor Morita. Paper is now open for discussion. Do you have any questions or comments?
Yes,
チェンコバ先生、どうぞ。
I have a congratulations for Morita Sensei. It's an amazing system that you have made. Congratulations. So you have this LC NIR. I haven't heard about this. Is it your new idea? Yes. And I can see that you have so much data now that you can do so many different angle calculations from different angle. And you can understand so much about it. I'm really happy about it. Congratulations.
Thank you very much.
It's beautiful work and very good idea.
Thank you very much.
That will contribute to aquaphotomics immensely. Thank you. Yes.
Very good bands, very informative. we have those bands actually related to the water activity. So about the mixing, about whether something is going to be endothermic or exothermic mixing. So this is very beneficial. Thank you.
Any questions?
Yes.
Please.
Regarding the slide 7, may I see it again, please?
Yes.
Maybe it's a silly question, but I ask it anyways. There is such of a waste in the blue and the green line. So the number first gets lower and then gets high again. Is there any meaning in this shape of the lines?
Might be the how can I say, the effect of the combination mode of such the additives having the small intensity, therefore, and the lower concentration of water affect such the small effect might be. Okay.
Okay. Thank you. Yes.
Any other questions?
Morita Sensei, do you take simultaneously all this data that you can take with LC, like electroconductivity? You have all this data, right? For each sample, for each time?
No.
No, you don't. It would be very nice if this also could be combined.
Yeah, might be. Yeah.
Thank you.
Any other questions? Professor Morita,
Yes.
if you change the pH of water, any other changes can you observe?
Thank you for your comment. We can recently do the experiment, but no data today.
Okay. It's very interesting, especially basic molecule can react with proton easily.
Yes.
So maybe you can find any differences.
Yes, thank you for your comment.
And we need so much to assign exact bands for protonated water conformations. Because for biological systems and for biocompatibility, it seems to be crucial to know those bands and to know those conformations that are contributing to proton wire and protonating. Yeah. Very good idea for pHs.
Any other questions or comments? We have 1 or 2 minutes.
In that case, I have a comment. I really like this. Thank you, Professor Marita. This was really a very nice study. I wanted to say that what I saw from your presentation about the electronic structure of these compounds. Recently, I actually found out from totally another scientific field, the people were investigating the hydrated electron, actually, which is a hydrated p electron, one which is, how can I say, pushed out of the p orbital by the use of very intense light, like laser and so on. So what they saw is that this hydrated electron, which is a very, very fast transitory species, absorbs at 1250 nanometers. So I'm not sure how can I now say in, so it is around 8,000 centimeters to minus one. So the other thing that they noticed, so because essentially this hydrogen electron is, it means polarization of ionization voltage, so separation of charge. So wherever we have this hydrated electron absorbing, we have information about the protons and protonated water. So this is my comment because I'm not sure what is the origin of the signal in this what we call combination band. So what we when we are using this bands, these bands around 1250 nanometers, this is what we call overtone of the combination band. And I was thinking maybe if you can have a comment.
Okay, thank you. So it is very difficult to understand the combination mode recently, so
I
thank
see.
you very much for the comment.
Thank
Yes.
you.
Okay, now time is coming. So please move to the next speaker. But unfortunately, Professor Shiraga is absent today due to his health conditions. So we will skip his presentation. And so the next speaker is Professor Ma from Nagoya University. The presentation title is Study on the Dynamic State of Free Hydrogen Bonded Water with Wood by Near-Infrared Hyperspectral Imaging. So if you are ready, please start, Professor Ma.
Thank you very much, Professor Takeuchi, for your kind introduction. I deeply appreciate to have this chance to join this great conference. Many thanks, Professor